Now we want to make our intuition precise. What we do now, we define a special random variable. So our random variable yi is defined as minus log 2 of px of xi. If we do it in this way, then we can write this here in this form. So we had this before, and now we just insert this yi here. So now we can compute that the expected value of yi is equal to the entropy. It's very easy to see because it's the same as expression for which we showed that this is the entropy, and this is nothing more because it's equal to this here than the expected value of yi. So the expected value of yi is h of x. So yi is a finite number, and we call it sigma square. And the weak law of large numbers is now this here exactly. So it says that the average, that this is equal this part here minus the expected value h of x is that the probability that this is smaller than epsilon is greater equal 1 minus sigma square divided by n times epsilon square. This theorem is the weak law of large numbers. You should know it. Perhaps Abdallah can go into details in the exercise. So Shen now defined xn to be typical with respect to epsilon and px if this is valid. So we choose some small positive epsilon and call this epsilon typical sequences. And if this is valid, then the sequence xn is called epsilon entropy typical. So you see that this value here lies between h of x minus epsilon and h of x plus epsilon. And this set of entropy typical sequences is called t tilde and epsilon of p of x. And this entropy typical sequences have some special properties. We see them here in this theorem. So we choose again epsilon bigger 0, and xn should be an entropy typical sequences. And we have this discrete memberless source, px, and we have a sequence xn, which is emitted by this discrete memberless source. And sigma square be the variance of px of x. And then we have the following three properties. The first property is that the probability of these typical sequences is lesser than 2 to the minus n of h of x minus epsilon and bigger than 2 to the minus n h of x plus epsilon. That means somehow approximately the probability is 2 to the minus n h of x. Now let's, with help of 4, you will see later, we can calculate the cardinality of the typical sets. So what does it mean? So the number of typical sequences is bounded by 2 to the n h of x plus epsilon from above, and by 1 minus sigma square over n times epsilon square times 2 to the n h of x minus epsilon from below. So that means approximately we have 2 to the n times h of x typical sequences. Now we look at the probability that the sequences emitted by the source is typical. So this probability, of course, every probability is bounded by 1, but you see it's lower bounded by 1 minus sigma square n times epsilon square. And this term here goes to 0 if n goes to 0. That means approximately for large enough n, the probability that a sequence is in the set of typical sets is near to 1. And that is in principle what we want. We find now some smaller sets on which all the probability lies. Perhaps there are some sets even which higher probabilities than the sets which are in this big set. But if there's only a single sequence with higher probability, like we saw in the example, for example, the all zero sequence have a very high probability, but it's only one sequence, then it doesn't matter. So what we want to look only on the set of sequences where more or less all probability lie.